So, so far we have discussed different analog amplitude modulation schemes. So, let us try to list all that we have discussed so far. So, one is basically DSB-SC, that is the first one probably we have discussed, and then we have seen a simple variation of that. So, that is also a DSB-SC, but we add some carrier to it. So, we can call that as amplitude modulation or just simple DSB with carrier. Okay, so this is just a derived version of that. And then we went towards more bandwidth efficient modulation schemes, which are single sideband, maybe suppressed carrier, maybe with carrier. So, we will see that also. So, every modulation schemes that we can think of will have suppressed carrier, that means you do not add any carrier. So, in the frequency domain there will be no delta term at omega c, which is the carrier, or it can be with carrier. So, there will be a delta term. And then we have talked about another one which is called VSB, vestigial sideband, maybe with suppressed carrier, again maybe with carrier. So, it might be just SSB, VSB with carrier. Okay. And then finally, we have talked about quadrature amplitude modulation. So, these three actually comes under, or I should say comes under bandwidth efficient modulation, and the corresponding version where we add carrier. So, those are with carrier, and wherever we are suppressing carrier, that we write with this term SC. Okay. So, let us try to see the means just a comprehensive summary of all this, the relative advantage, disadvantage, what can be done, what cannot be done. Let us just try to summarize all these things, because we have already covered all of them. So, for DSB-SC in time domain, suppose I have a modulating signal or you can call that as a message signal, which is MT. Always remember that whenever we are trying to modulate it, it has a corresponding Fourier transform in frequency domain, and that must be band limited. So, the frequency components are defined up to it is mostly baseband signal whenever we are talking about, and that is band limited up to B bandwidth. The significant frequency components are there. Beyond that, those are all insignificant or nothing is present. Okay, so that's our assumption. So, modulating signal MT, and if I wish to represent DSB SC, so we have already seen that in time domain the representation should be MT cos omega CT, right. It is just a multiplication with respect to a cosinusoidal term. Correspondingly, the modulated frequency domain response will go around plus Fc and minus Fc, and the shape will remain the same. If I just talk about another version AM, then I add a carrier to it. So, it is A cos omega CT plus MT cos omega CT. So, we are just trying to now summarize everything and try to show what we have achieved so far. So, it is nothing but A into A plus MT into cos omega CT. So, therefore, it is just like a DSB modulated signal, but the modulating signal you add with a DC level A, or actually in circuitry you add a carrier to it with strength A, okay, or power A square by 2. So, what will happen? The corresponding spectra will just look like DSB-SC at Fc at minus Fc, but there will be a carrier added to it. That is the delta function which is being added. So, this is something we have seen. Probably in that course of our discussion we have not talked about something which will try to reveal, but before that let me just characterize the other things also and then we will reveal that. Okay. So, for SSB SC, what we do is, of course, the MT will be there and that needs to be multiplied by cos omega CT, but then we actually that same message signal should be passed through a Hilbert transform and or go through Hilbert transform, and correspondingly we get MHT after getting a Hilbert transform of the message signal, where Hilbert transform we have already characterized. It is nothing but introducing or adding a phase pi by 2 for each frequency component irrespective of the frequency component. It is always adding a constant phase. Okay. So, this will be plus or minus depending on whether we are targeting USB or LSB, means upper sideband or lower sideband, and this should be multiplied by sin omega CT. So, the corresponding frequency domain response should be either this, that means only one sideband at carrier FC or minus FC will be there, or the other sideband. So, this is the USB upper sideband and this is the LSB. Okay. So, either this one or this one. Okay. So, whatever I was mentioning just a few minutes back, that there is something we have not talked about. So, the thing is that here whenever we represent this, you can see that it has a predominant representation, that a particular signal multiplied by a cosinusoidal term of the carrier and some modified version of that signal multiplied by a sinusoidal term, right. So, this is what is happening. So, this whenever we multiply with the cosinusoidal of the carrier, whatever we put over here, that is we call it as in phase term, and whenever we multiply with sinusoidal, we call that a quadrature term or Q term. Okay. So, this is in phase and this is quadrature, or we simply call that I or Q. Okay. So, for SSB SC you can see the in phase term is MT and the quadrature term is the Hilbert transform of MT, whereas for DSB-SC the in phase term is MT, quadrature term is 0, nothing is there. Okay. For amplitude modulation the in phase term is A plus MT, so a DC added to the message signal and there is no quadrature term, that is all is happening. So, this is just characterizing the signal. For VSB-SC again we have seen, so we are just trying to summarize again. So, it should be MT cos omega CT, okay, plus some MVT. This is actually that filter we were talking about, right. So, for VSB-SC if you remember what we have said, that we will be generating a DSB signal, then pass it through a filter, band pass filter, which is characterized as, or the transfer function is HIF. Okay. So, we are talking about this filter. If we just pass it through that particular corresponding, and corresponding to that there is a filter, and we can get a representation of MVT, which was we have represented that filter as FF, right. And if I pass my message signal through that filter, whatever I will be getting, that we term as MVT. Okay. So, we have already done these things. So, this can be the next represented, the modulated signal can be represented as. So, again we can see there is a in phase term and there is a quadrature term for this, and for both SSB and VSB-SC we can add carrier signal at any time if we wish. So, the corresponding signal should look like, so if this was SSB, so it should be something like this. Okay. So, that should be the VSB-SC, and then we have talked about QAM, which actually takes the entire band, but it represents two signals. So, basically what we have said, if we have a message signal M1T and M2T, then we can represent this, that M1T we can put in phase term and M2T in quadrature term. So, I can just write m1t cos omega c t plus m2t sin omega c t. So, that is in a nutshell. Of course, the bandwidth will look like same, but it will be just added part, the frequency response will be added with respect to m1's frequency response and m2's frequency response, right. So, that should be the case, but we have seen already, we have demonstrated that this can be very clearly separated out. Okay. So, that can be done. So, this is something we have already seen so far, and we have means these are the versions or variation of amplitude modulation schemes that we have. Now, if we just compare them, let us try to compare these things. So, if we just write AM, DSB-SC, SSB, we can write SC, general SSB also we can write, VSB-SC, and let us say QAM, right. Now, let us try to see where these things can be used. Of course, we can also have a just VSB. Okay. So, AM generally used for broadcasting, okay. Because we have seen that whenever we use AM, and if we have this condition that my A is just greater than equal to for all values of t, as long as this is happening, I know that I will not have any phase reversal. So, just by envelope detection with a diode followed by a charging and discharging circuit, I can actually demodulate it. So, the detector circuit becomes very simple, and that is why probably I will be targeting this for a broadcasting system, because everybody will have the receiver, they are not transmitting anything, it is just receiving things like television broadcasting or radio broadcasting that used to happen earlier. So, it is in that case I will probably employ this, because the receiver which is at the user premises will be more cost effective. So, that is something we have already seen. But of course, because we had to add that carrier, so this will not be that power efficient. So, we have also seen that if we talk about, so this is scenario where this can be used. Right. So, next if I talk about power efficiency, this is probably not that power efficient. Of course, the corresponding DSB-SC will be much power efficient, because I do not have to add that carrier and unnecessarily means we have already demonstrated that, right, with the modulation index, and then we have also talked about the power efficiency. So, this will be power efficient. SSB-SC definitely will be power efficient, because there also I am not adding carrier, but here we have already shown that if we wish to add carrier and then we want to demodulate, probably a huge amount of carrier has to be added. So, here if I wish to add carrier and we want to demodulate through that envelope detection, A must be much greater than this MT. So, the amount of power that will be wasted for transmitting carrier, which is not useful means signal. So, there will be wasting huge amount of energy, right. Again VSB, original VSB will be power efficient or energy efficient I should say, this will not be, okay. So, here also that same condition as we have stated, probably not proven. For SSB we have proven, similar argument will come for VSB also. There also A must be much bigger than this MT, we will be able to show that, because it is almost similar structure. So, this can be again proven. So, of course, this will not be energy efficient, and even what will happen, this SSB and VSB, if we wish to do for means use them for broadcasting, then definitely we will have to means operate at very low power efficient scheme, okay. So, that will be always happening. So, if we wish to do that, we have also proven another thing which is called the carrier recovery. Can we do carrier recovery or we cannot? this one actually does not require carrier recovery. It does not require, because I can, whatever happens, because I am doing amplitude modulation, so carrier recovery is not required. Carrier is already inbuilt. I can just put a diode, and we have demonstrated that that acts as if the carrier is already there and we are demodulating it. So this does not require. So I can say not required. Whereas for DSB-SC, yes, carrier recovery is required. That's a big circuitry. We have already started talking about the carrier recovery. We have promised that next we will be discussing phase lock loop, which is integral part of carrier recovery. So the DSB-SC definitely require carrier recovery. SSB-SC, this is where there is something that we have proven in the last class, that this for SSB-SC the carrier recovery is very difficult. For DSB-SC we have seen that we square it, we always get back the carrier, but for SSB-SC and VSB-SC, even if we square, you do not get the carrier term, pure carrier term. It will not be at 2 omega CT. So there will be a phase variation with respect to time, so you will not be getting the pure carrier. So carrier recovery is not possible. Here also it is not possible. That is a big blow in modulation technique, because these two are really efficient in terms of bandwidth. SSB particularly, it gives us twice the benefit, right. So two signals I can put in place of one signal compared to AM and DSB-SC, whereas VSB-SC not that much efficient as SSB, but okay, it gives some benefit. But the problem is I cannot really, and they are also energy efficient because I am not putting carrier to it, but I cannot really do carrier recovery from them. The original signal that has been transmitted, from there I cannot extract the carrier. So all I will have to do, probably I will have to separately transmit pilot carrier along with them if I wish to do demodulation properly. So that is a additional headache that we will have to take if we wish to do that. These two, okay, carrier recovery means I am putting carrier, so it is possible that I do not have to do carrier recovery, I can just do same envelope detection over here, but energy efficiency is very low. That is what happens. Okay. So these are the few things that I wanted to discuss. Means this is something we have already covered, we have proven all of them, but I wanted to summarize them. Next, another one thing probably we have discussed, that is actually related to the carrier mismatch. Okay. So there are two mismatch we have seen. These are the things also we have demonstrated, that there might be a phase mismatch between the incoming carrier and the local carrier that has been generated. Once we will be discussing this PLL, you will see that that is possible, that might be happening. So if there is a constant phase mismatch between the incoming carrier and my locally generated carrier, whichever way I can square that, pass it through a PLL, whatever carrier I get, if that has a constant phase mismatch, then what will happen? So if I have phase mismatch of delta, and then we have also discussed a frequency mismatch of some delta. Okay. So this probably we have given as some delta and this something like this, right. So if I have a phase mismatch, what we have seen for this one DSB-SC, we have demonstrated already. What we have seen, that probably will get the signal intact, but only thing is that there will be a attenuation of this term cos delta. So modulated signal, after we demodulate, I will get back my MT, but MT will be multiplied by this cos delta. Now the problem is, if the phase mismatch goes around pi by 2, then this cos delta will be 0, so attenuation will be very high, I will not get my signal back. So that is the detrimental effect that will have. But if there is a frequency mismatch, what we have seen, that this will be multiplied, my MT will be multiplied by cos delta t. So there will be a modulation term which will be, which will vary the essential nature of the message signal itself. So that's little more detrimental. So if there is a frequency mismatch, I have to be very careful about that. So I cannot really allow frequency mismatch in the incoming carrier and the local carrier I am generating. All these things will be very clear in PLL. We will see the strategy that we have to take to ensure these things, knowing that this will be happening. Then for QAM, we have discussed some more things, that if there is a phase mismatch, so we have already seen that okay, probably it will not, means the message signal will have something like that M1t, suppose I want to demodulate M1t, so it will have this cos delta term, but there will be also additional term with respect to M2t. So that will actually give me interference to my signal. So that's even more detrimental for QAM. So QAM in terms of phase mismatch and frequency mismatch, it's more vulnerable, because I am actually modulating two signals and putting in the same band. So I will always expect, if there is a phase mismatch, immediately there will be a interference term coming from the other signal which will corrupt my signal. So that will happen, whereas for phase mismatch in DSB nothing will happen, okay, it will just have attenuation term. Same thing will happen if just you carry on the same technique, you will see that it will be just repeated over here also, it will have similar effect as DSB-SC. Okay. So VSB or SSB, if you carry out the same thing, you will see that similar effect will be happening for them, but QAM, that is more detrimental. So if you just modulate with respect to QAM, or if you are transmitting with by employing QAM, you have to be very careful about the frequency and phase mismatch in your local carrier. Okay. Frequency mismatch, of course, there will be modulation, interference term, plus there will be additional modulation term which will be coming out similar to this. Okay. So these are probably what we have discussed so far. Okay. So just if we summarize that where what can be used and what are the things that I need to take care of. So whether it's energy efficient, whether carrier recovery is required, not required, accordingly the receiver circuit how it will be, can we use it for broadcasting, can we use it for one-to-one communication or point-to-point communication, and if there are in the carrier recovery, if it is required at all, that means I cannot employ means envelope detection, then what kind of effect I will get if there is phase mismatch or frequency mismatch. So this is something we have so far discussed. There were some more things which has to be which we have also discussed in the process, that was related to two of the bandwidth efficient schemes. So one is SSB, let us say SSB-SC, and the other one is VSB-SC. So we have seen that this is good for if we employ a Weber circuitry. This is good if we have a signal which has nothing around 0 in the frequency band. So that means voice signal. So this is good for voice modulation, but this is not good for video modulation, because that has something. So video spectrum looks like this, whereas voice spectrum looks like this. So nothing around 0. Okay. So for this SSB-SC is good. We know that SSB-SC can be generated by filtering approach. Okay. So for that filtering approach only we are talking about this. For the other approach where you have to take Hilbert transform, that is very difficult, because every frequency component has to be given pi/2 phase shift, which is very critical, and that is very difficult to realize in realistic circuit. We have given an alternate circuit which is called Weber circuit, which is with respect to filtering. So you do first filtering, then you modulate, then you do another filtering, and you get your signal, right, modulated signal. So for that we can only modulate voice signal, we cannot really employ this technique for video signal, whereas VSB was actually designed keeping in mind that if a signal has something around 0, what should we do. So, this particular thing can still be realized using a realistic filtering technique, okay, because it allows the filter to have some roll off, some realistic roll off. So, that is something which we have discussed so far. Okay. So, now we can see that the only part which is still not very clear probably is the carrier recovery. So, we have to now discuss in big details about the carrier recovery and what is the consequence when we get some phase delay, when we get frequency delay, sorry, so when we get some phase delay among the carrier and the locally generated carrier, or some frequency deviation among the locally generated carrier and the incoming carrier. So, in the next class what we will try to do, we will try to get into inside the PLL circuit and try to see what happens over there and do some analysis. Okay. Thank you.